So the first part of building logic in Python, it would be very useful to have a data type that could help us. And so that's what leads me to talk about Booleans. And Booleans are very convenient because for logic, they can be either true or false. So let's start with a very simple logic test. So we do print 3 equals 2. Right, so what would we expect? We would expect this to be false. False, great. Our intuition is correct. So what's happening here is 3 equals 2. This expression is being stored as a Boolean. So we can define a new variable, my bool. Let's try 3 greater than 2. Okay, what is... We evaluate this, great. It's stored in the variable myBool. Now let's print what this variable value is stored. And we get true as expected, great. So this is a nice introduction to what Booleans are, and we can do some nice manipulations to evaluate logical statements. And a simple logical statement is an if statement. So let's try the example of water, or the temperature of water, and what state of matter we would expect for water based on its temperature. So we can do temperature equals -1, and -1 makes sense in this case. I can't spell, so let's do temperature. And -1 makes sense because it's Celsius, great. So 1 degree below 0. So let's do an if statement. So we start by saying if, and then the logical expression we would like to evaluate. So if temp is greater, then let's try 100 degrees Celsius. Then we can say print boiling. So this is, we've just evaluated this logical expression. And because we've set temp equal to -1, we know that it's not boiling, right? So let's try 150 degrees Celsius. What would we expect? Well, it's greater than 100, so it should be boiling. Wonderful. So far, our logic seems to be correct. Okay, so we can go back and actually add more tests to our if statement. And in the materials project community, we like the analogy of a funnel. So, and that'll become a little bit clearer here as we build on this if statement. So in this case, we have a filter. We're defining a filter where if the first check is the first logical check, and then we can have a catch-all statement, an else case, which is everything except everything that does not fall is not caught by this if statement. So we can say if it's not boiling, it's not boiling. So let's print this out, not boiling. We can go back to change our temperature to negative, close to absolute 0. So 273 degrees Celsius, not boiling. Great. So far things seem to be working. Now we can also add what are called else if statements and make our if statement a bit more complicated and capture more logic. So this can be written in the form as elif, stands for else if. Temp is greater than 0. We know that it would have to be a liquid. And why is this? Well, because it's not boiling. Oh, increase text size. Okay. Okay, I'm trying to, how does one go about that? Okay. There, I hope that's better. Maybe that's too much. Okay, so I hope this is easier to read. So I was asked to increase my text size. Okay, great. So so now we've increased the complexity of our if statement. So what do we have here? So if it's not boiling, so it's not greater than 100, but it's greater than 0 degrees Celsius. It's not freezing, it's not a solid, but it is a liquid. So we can add this as well. So we've captured all the states of matter for water in this case. So it's for this, as we would expect, for absolute 0, we would expect it to be a solid. So, and if we try 200 degrees, we get boiling or gas to be consistent. Great. Okay, so this is our filter or our funnel where the first check tests, okay, is it greater than 100? No. Okay, is it still greater than 0 though? And if yes, then liquid. If else, it's going to be ice or solid. Okay, so let's see, I have a bit more time. So now let's go in and talk about the typecasting, some of the typecasting properties with Booleans in Python. So some interesting things of how Python deals with if statements when you have variables that are non-Boolean. So to illustrate this, we ask, what is truth? So if we typecast, and Ryan touched on this, but if we want to set a variable, say the integer 5 to bool, what do we get? We get true. So this is interesting. So 5 maps to true. If we do 0, we get false. Interesting. What if we do -5? True. So all the integers not equal to 0 are mapped to true, where 0 is mapped to false. Okay. What if we try string, which, as we learned from the last lesson, is a list of characters. So is true. So a list or a string in this case is considered true. Now, if we do an empty string, we get false. Interesting. Okay. So if we do, let's try an empty list. False, as expected. Okay, let's try 1, 2, 3, 4, and maybe MP. We get true. Interesting. So if a list is empty, we would get false. If it contains elements, then it will be set to true. So this is an illustration of the falsy nature of Python, which is a cute term to describe this, but it helps us when we want to write if statements. So if we want to make sure that a list is true, my list, in this case, 1, 2, 3, then if we do if my list print, and we can do a print statement to make sure we've entered this if statement here. Great. And if we leave that empty, we do not enter this if statement. And there's another illustration of this. If you have defined a variable, you want to be careful in Python because we don't always want to map variables in a certain way between Booleans and their respective data types. Okay, great. So let's clear this. And now let's move on to the exercise. So yes, please ask in the chat if you have any questions regarding this lesson. But now let's move on to some of our exercises. So this is a nice illustration of how we can use our new discovered if statement to create a temperature conversion, unit conversion between Celsius and Fahrenheit. So here's an illustrative example, and feel free to fill it in, and there's solutions included as well in the same directory. So here we have this example where you can actually pass in, and this is a nice function. So it allows the user to pass in a value to the program, which is evaluated and set to temp. So what we can do here is if we run this, well, let's first fill it out. But here, if this upper function is taking, so it's essentially taking the last character of the string that is passed from the user. So in this case, if we pass in 45F, that is interpreted, or we want it to be interpreted by our program as 45 degrees Fahrenheit. So this convention upper, so it takes the last character in this case, and it denotes what degrees or what temperature convention we would like to use. So in this first case, we see that it's Fahrenheit. So we would expect the character to be F to represent Fahrenheit and C to represent Celsius. Great. And so we have this if statement here that takes our convention and then produces the respective conversion that we would like. So if we run this cell, we get the nice prompt here, prompting the user to enter in their temperature. So we can enter in, say, 200 degrees Celsius. And if we press enter, we get 93 degrees, 93 degrees Celsius, which maybe we did something wrong here. Yes, so this was my mistake. It's actually, we want these reversed. So it's not, this is the O convention is what we would like to produce. So F. So then let's try that again. There we go. So hopefully some of you caught that. It's a bit of a test. But yeah, so this is actually, so our I convention is the input convention, and what we would like is the O convention, or our output, what we would like to convert our input, what convention we would like to convert our input to. Great. Okay. So yeah, maybe I sort of jumped into this one, but maybe I'll take some time, a couple minutes, to allow for the next exercise to let you all have some time to go through and test it for yourself, test your skills. So this next exercise, essentially we use this data, which I'll talk about a bit, and then you can fill out the logical statements. So we import this dictionary, which includes the names of the elements in our periodic table. And in that sense, and we'll talk about dictionaries a bit more in the next exercise. But if you once you have this discovery dictionary, you can based on the element name that you place and index how you index. So it's similar to lists in that you can index this directory with the element name, and you can get the names of those who are credited with discovering this element. So we can talk more about dictionaries in the next lesson, but just as an illustrative example, you can enter for discover 0 and discover 1, the two discoveries that you would like to discover or explore, and what elements are credited to these discoverers. Great. So we can, once we get A and B, what would A and B be in this case? And this, I'll leave a few minutes or a couple minutes if time allows for you to figure out what A and B if A and B are Booleans, what would they have to be to check if this name is equal to our discoverer 0 or discoverer 1. So go ahead, and I'll take about a minute for you to think about this. Okay, and now just because I would like to go to the next lesson for time's sake, we can go through and fill this out. So A in this case would be is, so A and B, we'd set these first to false. So this is a bit tricky, but if we're going through the names, we want to see if our discoverer A is Berkeley and our discoverer 1 is Russia, where these are regular expression strings for the names included in our database. So A in this case, so if discoverer 0, so the string 0, so Berkeley in this case is in name that we found, then we can go through and say that A must be true, and B in this case must be true. So these are saying, okay, we're going through the names in our directory. So we're iterating over the elements in our dictionary, and if our discoverer name matches or is in the array, in this case of characters or a string, this is a nice Python formal way of saying if the substring is in the string, then A is equal to true, or vice versa, or similarly, B is equal to true. Okay, so now let's do our if statement. So we can see by what's printed what these would need to be. So if A and B, if A and B are not both true, what would be the next case? The catch case for if A and B are true. So we can put in either A or B, but in this case we see our string that's being printed is A and B. Great. So let's run this. Dictionary is not defined. So I did not run these cells before. So if I run these import, and we can load in, I believe Ryan touched on this, but we can load in data in the form of a dictionary, which we will talk about next. But so we can go through our elements, and we can say for this element, we only print it when so we go through all of our elements and we print when this if statement is matched. So for the first, B is true. So scientists in Russia are credited for discovering borium. And then it's interesting for this element, A and B are true. So that's interesting. So scientists in both Russia and Berkeley are credited to discovering this element. Now you may be noticing there are quite a few elements missing from the many elements that are credited to Berkeley scientists for their discovery. So we can include the name of a famous scientist who was working at Berkeley for a period of time. And we see that the number of elements increases greatly. So it's not perfect, but it depends on, there's overlapping sets in this case of who's credited with what. So yeah, I'll let you play around with this. I hope this was a helpful example. And I hope that online in CoCalc, everything's going smoothly. And now I'd like to move on to the next lesson, which is transitioning into talking about dictionaries and sets. So how do we initialize a set, and what is a set? So a set is similar to an array. However, sets store unique values, which is a nice property. So let's define a set of prime numbers, which we will include the first 4 prime numbers, 2, 3, 5, 7. So we see here that we've defined this set. It likes it. Python likes how we've written this. And we can print is 3 in primes. So that will be our Boolean. And I touched on this before, but Python has this nice, very succinct syntax for checking if an element is in a particular array, set, list. So we can do this. We can test if 9 is in these primes, and 9 is not in the primes. It's not a prime number, and it's not in the prime numbers that we've initialized. Great. Now let's include another set. So we'll include the odd numbers. And you could, if you were so inclined, you could go, up to infinity. But it's not really necessary. And there's ways of actually going through, we might touch on this, but of automating that process. But let's run our cell. So odds equals these numbers. Great. Now there's a nice additional syntax for computing the intersection between two sets. So let's print what the intersection would be. And this could be, so the intersection uses this symbol, the and symbol. And we see that the set that results is an intersection between the primes and the odd numbers that we've defined here. So this is really nice. So if we have 2 sets, and this is also convenient if you have a large number of sets with unique, and they store unique values. So we can play around with some set theory and actually go through and also, we can also do, copy this down, and you can also look at the union between the odds and the prime numbers. So this is sort of an and or operation for sets. So these set elements, as you can see, are the union or the combination, the unique combination between odd and prime numbers that we've defined up here. Great. Now let's move on to another property of sets, which is important. And Ryan touched on this previously, but the concept of mutability. And mutability is the ability to, once you've defined a set, can you go back in and modify the values? And the answer is no. So, or I'm sorry, sets are mutable. I'm thinking of tuples. My apologies. So sets are mutable, and you can go in, and if you have your set of prime numbers, we haven't included all of our prime numbers. So we can add a prime number to this set, say 11. And if we print what our new set is, we get the prime numbers from 2 to 11, as expected. We can also discard. So in this case, if we discard the element 7, we see that if we print the primes, we get all of our prime numbers minus or without the number 7 included. And finally, I'm going to go ahead and copy this, but we can also add an element, or we have that, yes. But we can add another element. So if we added 11, we can also add, say, 13. Another property of sets is that they are unordered. So although they store unique values, once you add in or discard an element from a set, they do not reorder themselves. So let's define a set of names. Some names of famous scientists, which may or may not be familiar, but hopefully they are. So we get the names of these 3 influential scientists, and we can loop or iterate over these names. Okay, so I've made a syntax error. So n in names, print. Great. Okay, and I think I'm a little over time, so feel free to go through the rest of this notebook, and you can we can go over dictionaries. I might take a moment or so to go over a dictionary. So what a dictionary is, it's essentially a set, but you have a key value mapping or key value pairs. So if you have a set of birthdays for these famous scientists, or the birth year, so for Hopper, the birth year is 1906. For Corey, we have her birth year is 1896. Great. So we've defined a dictionary here, and we can go through and iterate over this dictionary or index this dictionary using the keys, which are defined here as Hopper and Corey. So if we print what the birth year of Corey, okay, birthdays, we would get 1896 as expected. So this is very convenient. Dictionaries are very convenient for storing these key value pairs and storing essentially a mapping. If you have a set of values associated with a set of keys, or a set of items formerly with a set of keys, then we can index, instead of going through it and finding the exact index in the list, we can actually index this dictionary using these helpful keys. And this is a nice property, a nice data structure of Python. So going to check the time here. But yes, so we have until 11:20. So the next part, we can come back to this lesson, but I'd like to make sure we get to the exercises. So let's look at our exercises that we have for this lesson. Okay, so this first exercise is based on creating a histogram if you have a set of, or a list, I should say, of numbers. How do we look at the distribution of numbers within this list? So one way of doing this, using a dictionary, is to create an empty dictionary and iterate over these numbers and bin them accordingly based on the keys that have been defined within our count dictionary. So we can do this in the following fashion, but maybe I'll take a moment to allow you, I'll take a minute or so to allow you to think about what this if statement would be. And I'll give you a hint. So one way of doing this, and I'll create a new cell here. So one way of doing this is if we have a list A is equal to 1, 2, 3, and we want to see if the element 4 is in this list. If 4 is in A, we can print here element in our list. We evaluated this if statement, or this cell, this code block, and the if statement was not evaluated. So that implies we could add an else statement, as you know, or as we've learned. But let's, for simplicity, go back and try 3 instead. The element is on our list. Great. So this is a nice way of checking if it's in our list. Similarly, for dictionaries, we can create a dictionary, and we can have keys that are not only strings but are also integers. So we can have a mapping between integers, or keys and items in this case. We'll say, and then we'll define. So we have the keys 0, 1, and 2, with the associated items 1, 2, and 3. So if we try, is 3 an A? It is not an A. So let's try 2. Element is our list. So essentially what's happening here is this if statement is asking or inquiring, is the associated key defined or declared here in the dictionary A? So we can also try 0, and 0 is also in our list because we've previously defined it as a key. So this gives you a bit of a hint, but how would you fill in the blanks here? And such that we create a histogram where we bin the numbers, the values in the numbers list accordingly. Okay, so as you can see from this hint down here, we can see that this if statement would be if n not in our dictionary that we've defined as count. And a nice property of dictionaries is that you can, although the keys themselves, so in this case 0, 1 for A, 0, 1, and 2, while those are immutable, cannot be changed following the assignment, we see that the items themselves can be updated. So the item associated with count at the key n, which corresponds to, and in this case corresponds to our bin. So if we evaluate this, we see that we obtain a dictionary that is very nice because it actually has the number of reoccurrences of those numbers. So if we look back at our numbers list, we see that for the number 1, we have 5 occurrences in our numbers list. We can verify that by looking at our list. So 1, 2, 3, 4, 5 looks good, and we can verify so on and so on for the other elements in this list. So we see that up to the integer 3, there are no other. So between so 1, and these are not ordered. so we have 1, 0, 2, and 3 occurring in our numbers list. And this if statement is the binning action. So if n is not defined in count, it hasn't been binned, then we set it equal to 1. So we found the first occurrence of n. Else, and this else means that n is in count. And we could also flip this if statement just as easily, right? So we could do if n in count and have these two cases inverted, and our if statement would be just as effective. But in this case, if it's not in count, it is in count. So we update the binning of our numbers list, and we increase the count or the number of pings of, hey, we found another occurrence of this element or of this number in our list. Okay, so let's move on to the next exercise. Well, first, beforehand, there's this nice collections library where you can essentially compare and check your histogram using this counters class, or which might be touched on later in this workshop. So as we see here, if we evaluate this block of code, we see that what would be the histogram predicted by, if we pass in numbers, our list, we see that it matches what we obtained using our little algorithm. So more or less, this is what this is doing. But there's probably something else more interesting happening under the hood. But it's a nice verification to make sure we're doing things correctly. The next exercise I would like to cover is determining the molar mass of a molecule. So if we have a list of tuples in this case, which are these key value pairs. So similarly to a dictionary, but we have it defined as a list here. We can iterate over these using our for loops, which Ryan covered in the previous lesson. And I'd like you to take some time to think about, if we have a molecule defined in this way, where we have the element symbol and the associated number of the formula number for that molecule, we can actually determine what the molar mass would be using this imported data, which is very helpful. So let's see. Let's first see what this data is, which might be helpful for completing this exercise. So if we have here, and I'll just import this down below. So if we import this data, it works great. We'll now see, okay, what is atomic weights, which is a dictionary, similarly to the previous lesson, that it contains the elements with their associated molar mass. So if we index atomic weights, let's try hydrogen. And it would be proper to print it, but I can just evaluate it, and it will be printed to the console, to the terminal. So here, our expected molar weight or molar mass is 1.00794, as expected. Okay, so go ahead, and if you have any questions, pose them to the chat. But I'd like you to try and think about how you could compute the molar weight using this information and the associated atomic weights dictionary that will come in handy. So I'll allow about, well, maybe a minute or so. It's a little short, but hopefully that gives you some time to think about it. Okay, so I hope you're not completely lost on this exercise. Yeah, so one way to go about completing this exercise would be to iterate over the species in our molecule and compute their respective contributions to the molar mass. So the solution is included. We should probably move on to the next lesson. However, if we look at the solutions, we see that we can compute the molar weight in this way using this simple for loop. So as Ryan described, you can iterate or create these iterables. You can define these two loop variables that are iterating over methane or our molecule. And the species and the number correspond to the pair, the species and number pair contained in these lists. And just a technical detail, these parentheses are tuples. So they're similar to lists. However, they are immutable. So they're meant to, once you define them, they're meant to stay static for the most part. So we can iterate in the following way over our molecules. And we can try our other molecule as well and compute its molar weight. And we see that our molar weight algorithm appears to be working, where we iterate over the molecule and add to the molar weight in the following fashion, where we have the atomic weights associated with each species, and then the multiplicity of those species within our molecule. Okay, so, and feel free to refer back to these lessons. You'll have them later with the full solutions contained in the exercise solutions notebook. But if you have any questions, again, feel free to pose it to the chat on Slack. Great. Okay, now let's move on to how do we create functions? Functions are very useful because they allow us to define an input-output function. So if we pass a set of input variables to a function, we would expect to get an output. Let's create a simple function to begin. So we start by defining def, stands for define our function, and we can say this is our hello world function. And these parentheses here, we won't define any inputs yet, but this is where our associated inputs would go, just for future reference. Hello world, my apologies for the typo. Print and if we've defined this function as expected, and if we call this function in the following manner, we get our output. Great. So this is a very simple function, but we know that things are working, and we can use this as a general format for how our functions are written and how they behave. So in this case, we have the definition, the function definition, and we have the block of code, indented block of code that will be evaluated once this function is called. And indentation in Python, it's important to keep in mind, is very important to how the code is evaluated. For instance, if we remove this indent, which is roughly equivalates to 4 spaces, but we can, if we remove this indent, we see that Python complains. It says, wait a second, there's an expected, actually tells you there's an expected indented block after this definition line. So we can bring back our indentation, and we see that everything works fine, works as expected. Okay. Now let's add some arguments to our function. And these correspond to the inputs that we would like that define what we output from our function. So let's define print date function. And we contain in our parentheses, we'll say our inputs will consist of the year, the month, and the day. And these will be in the form of, well, they can be different data types, which you'll see next. But we would like to make sure that they're typecasted to strings, because we would like to, in the end, effectively create a string that's a joined version of these inputs. So in a format that we would like. So let's go ahead and typecast the year. And another way of joining substrings together is the nice convention of the plus or addition operator. In the context of strings or characters, this corresponds to a joining of these substrings. We'll include the month as well, because we would like the year, the month, and the day. And we would like to typecast the day as well. And this converts, so if you, for instance, were to pass integer values to year, month, day, they would be typecast to strings. And an example, I'll just do this below. But if we have x equals 1 and we print x typecast as a string, we get 1. But if we, so it doesn't, when we print, print actually is sort of doing this, its own typecasting when it prints to the console. But we see that it is actually a string type. So it no longer has the same operations that an integer would have. If we want to be very careful as well, we make sure that x is indeed an integer to begin. Okay. So here we have our function. Let's go back to our function, and we will print the joined string. So this will be the operation that we would like to evaluate once our function is called. So let's go ahead and define our function. No errors, great. Now let's call our function with the associated inputs. Print date, just taking the time. Okay, let's try 1800. We'll do 7. I believe it's the 28th. Yes. So, and we'll call our function, and we get, as expected, the year, month, and day in this year of 1800. Okay. So let's see. There's a bit more to this lesson, but it might be good for you to, on your own, to go through and examine what these lessons are. So we won't be able to get to the full lesson, but one important feature of a function as well is you can include a return statement. So just for convenience, I'm going to copy this function below, and instead of printing join, let's return join. So this is the value that's produced by this function. So if we define this, we see that we can define my string and set it equal to the output produced by our function. Print date, and we'll include a different year. So let's say 1930. Great. And if we run this, we see that this function has produced an output that has been stored in my string. which as expected produces this output. Okay, so this is a brief introduction of functions, but you can also, as you can go through the lesson, you can see that you can, there's a lot more functionality. You can actually define unique or default values for each of these unique inputs. So now let's move on to the exercises as well. So the first exercise is the function of, if you input a list of values, we want to iterate over these values and return the first negative value of this list. So I'd like you to think about, based on what we've learned, how would you go about and fill out this function such that it performs the operation that we want it to? And I'll leave a couple minutes to think about how you would go about this. Okay, so we can refer to the solutions notebook, but I'll go ahead and input what, oops, my apologies. So what are we iterating over? We're iterating over our input values, which in this case would be a list of input values, and V is the element of that list. So if V is negative or less than 0, we would return that associated element. Hope that makes sense. Once again, so we iterate over the elements in our list. If that element is less than 0 or negative, we return V, the value. And the reason this returns the first negative value is, once we include a return statement, if this is evaluated, we will exit our function. So let's give it a test to see what's happening here and if it operates as we'd expect. So my list, and for convenience, we'll stick with integers. So we can do 1, 2, 3, 4, 5, and then include our negative number in there, and maybe some another negative number, negative 10, and 0, 4, 5. Okay, so this is our list. Hopefully it's sufficient enough. Maybe let's make the last one negative as well for illustration. And we will run our function. So number equal, we'll set this equal to the output of our first negative function. So first negative function, and we'll enter my list as the input. And then once it's the function is evaluated, we'll print the output. So -8 is the result, which we would expect, right? Because it's the first negative value in our list. So things seem to be working. So hopefully that makes sense. But so once again, to stress this, the return statement is only evaluated once. So once you return that value, the function is complete. You've returned the value, you've performed everything, you've gotten the value that you would like to return. So that's something to emphasize. So it's sort of a break statement as well. You can use it that way. So even if you have code under here, so print we never execute this print statement because we've executed the return statement. Okay, great. Let's see how we're doing on time. Okay, so now let's go to these other exercises, and for the sake of time, I'll leave this first exercise for you. But let's go ahead and look at an interesting property of functions, which is that they can actually be passed into other functions. So this example is testing if you have a chemical compound and you have the names of your associated classes of elements. And we define a halide to be a compound with a associated calcigen anion. Sorry, not able to speak today. And then we also have the anion is the least or the most electronegative element. So we can go ahead and if we pass in a crystal structure from our database, we can create a function that determines, is this crystal structure a halide? So this is a nice function that's been already built for you. So first we want to determine, okay, is this element a halogen? So this function determines if you pass in an element, you can use the function associated with the element class, which we import from PyMatchin. So now we're starting to use PyMatchin and the library developed by the materials project community, which is very helpful for looking at elements, for instance, or crystal structures, and many different material properties. So we can use the element class and its associated attribute, the isHalogen attribute, which determines, once you define the element, is it a halogen? Okay, so maybe we should test this first to see, okay, is this working properly? So this is a compound class that we'll fill in, but let's first test these existing functions. So we can go ahead and run this cell. So we can test if something is a halogen, right? So using our define element, define halogen input element function. And for illustration, let's try, okay, what is carbon? Is carbon a halogen? Oops. Okay, so I've passed a string here. So this is a good check. So so we're getting a string object, which is illustrative for us because we want the element input. So we want an input that is the class type element. So to do so, we can use this initialization of the element class and false. So C is not a halogen. Okay, great. So let's try sulfur, false. Okay, as expected. So now go ahead and using these existing functions, we can determine if a crystal is a halide crystal. So if we pass in one of our crystals, so we've imported this crystal database here using the JSON file format, and we can iterate over these crystals. So if we print the first element of this crystal list, we see that it is, so it has the associated chemical formula here, and the elements associated with this crystal structure, the space group information, and the crystal system. So let's try and pass this to our halide function, which takes in the elements in our crystal and sorts them based on their electronegativity. So this is essentially a convenient way of creating a list from a for loop, but it's a one-line for loop. So we're saying, take in my list, I would like all the element, and this, so we've taken the element initialized with the symbol for S in the elements within this crystal. So if we call our halide function on the first crystal in our database, we get that is equal to false. So, okay, so this is interesting. So it seems to be working, and I would have to go through the crystals, and we could see which ones are halide crystals, and you can iterate them using the following way. So you could essentially pass the index of the crystals. Crystals is a, if we print the type, it's a list, okay? And let's print the length of this list. Okay, so there's a lot of crystals to go through. So, and there's a later part of this exercise, a test your skills exercise, which I'll leave for your own development, or your own exercise to test your skills, that combines a lot of the things that Ryan and I have covered in an introduction to Python. And you can actually iterate through these crystals and obtain information about their molecular mass and their a rarity metric based on the rarity of the elements in the Earth's crust. And you can plot a nice histogram of this, and I'll show you what that looks like. So this is the molar weight, or the molar mass of your crystal structures, and it produces a histogram of those. And you have to go through and sort through your crystal structures using the skills that you've learned in these lessons, in these subsequent lessons. So if you're so inclined, you can go through and test your skills.